All right, so we wrap this up with quantum physics, quantum computing, both, because it's about as far out there as we are without getting into science fiction. And of course, there are aspects of it that do a little bit seem like it's getting into science fiction, but it's pretty real science. There's an awful lot of folks who are working in these areas doing a lot of really legitimate research, but they're not, and development, both. You know, we have tentatively working quantum computers, and the term working quantum computer right now means, you know, we think we've got the principles to the point that we can start making them compute on a regular basis. We're not quite to the point that you could actually put a label on it and sell it as a quantum computer. We'll talk about that a little bit more before we get done. But let's go back just a little bit. I don't know how many of these notes you've previewed or how much of it you know from other places. If it's stuff that you're real familiar with, just give me the old, you know, speed it up sign at some point, and I'll get through it a lot faster than I would otherwise. I'm not going to take the whole time in either case, but you ought to probably, you know, before we talk about it, probably get a little bit of background in case you don't have very much. So, you know, we started with not knowing very much about how the world works, and that went on for 1600 years, and then Newton came along, and well, longer than that, but I mean, when we were doing decent thinking about it, and then Newton came along and said, no, here are the rules, right, and laid out a bunch of rules for how objects move, essentially, and sort of updated what the ancients thought about how objects move, because the ancients pretty much based what they thought on how the heavens move, and not everything moves exactly that way. So Newton essentially, along with some others in that period, post-New Science, right? New Science works out a lot of it for him, but then there's the real hard stuff, and Newton comes up with a lot of it. There are some others in that period, but pretty much works out the big forces: mass, force, momentum, velocity, speed, acceleration, and out of all of that you get gravity. And, you know, you can take the classic Newtonian experiment on a billiard table and hit some balls, and they move around in predictable ways. And Newtonian physics works fine. If you take a physics class, you're probably not an IM major. If you take a physics class, you know, most of what you'll get is Newtonian physics, and it works real good for big stuff. Okay? And it worked, you know, pretty good until around the turn of the last century, 1900 or so. Just before and just after. So 20 years before, 20 years after is the period we're in here at this point. Okay? And there were a lot of folks along with Einstein. I've listed a couple. Einstein gets a lot of credit because he was real smart, and because he, in some ways, published first, and because in some ways there were unique insights that were his ideas. But there were other folks all around these ideas. Some of them even more spot on than Einstein. But he just put together the best package for all of it. Okay? He intuits, really, just sort of thinks it through as a mental experiment and then does some math. By the way, Einstein never did the math right in his entire lifetime. People came along and helped him along the way to make sure he got the math right. Okay? In fact, he published a lot of stuff that the math was wrong, but the insight was right. And then when the people did the math, the insight was still right. Okay? So first of all, we get the theory of special relativity. Okay? And that's that space and time are related to each other such that mechanical physics or Newtonian physics depends on space and time and their relationship to each other. So measurement of phenomenon depends upon the speed that you're going, and or the speed the object is going. Okay? Well, that's not Newtonian. Newtonian, you say, how fast that ball go, and you measure it. How far did it go, you measure it. It doesn't make a difference how fast you're going. Everything's fixed. You just take out some kind of measurement technique and you measure it. Einstein shows if you get on a really fast train, or of course it's been verified with capsules in space, and you're moving really fast, and you take those measurements, they're different than the measurements that you would take if you're holding still. That's because space and time are relative to each other. So essentially, science goes on its side at that point. Because everything we know is based on Newtonian science. And Einstein says, well, hey, your measurements aren't even right. Because you've never considered your motion before. Right? So, yeah, they're all consistent because the world spins at the same speed. But boy, once we get away from that basic physics, then we got a different problem. If you're on a plane, if you're on a train, if you're in space, if you're a spatial object flying faster or spinning faster than we are, everything changes. It's not absolute. Okay? Then, if that weren't enough, and it would have been, right, he comes up with the general theory of relativity. So, the special theory sort of undoes most of Newtonian science, right, physics, and then he comes up with this notion of how space and time are related with regard to curvature and gravity. We're looking for what the force is that is gravity, and we'd always sort of thought it was kind of this magnetism at the center of things or something like that. We weren't quite sure what it was. Right? And he says, it's a relationship between space and time. It's a relationship between space and time. Well, think of it this way. This isn't exactly right, but it gives you the right picture. Right? If you take an object like a bowling ball, and then you take an object like a blanket, you lay the blanket out like this and put 4 people in the corners or 12 people all around, however you want to do it. You put the bowling ball in the middle, the blanket goes like this in the middle. That's how space and time get warped by mass. Jeez. Right? So gravity isn't suck. It's more like roll down the hill. The Earth has mass and sort of things go in. Right? So, he just blows the whole thing away. We don't know anything now about physics. And then there's other people who go, yeah, he's right. It doesn't take near as long as it took, to say that Copernicus was right, which took literally a couple of hundred years altogether to agree with him. Einstein, they verified within about 20 years altogether. Okay. Now, neither of these are what he won the Nobel Prize for. Biggest ideas in the 20th century, neither of them are what he won for. What he won for was the experiment, essentially, that produced quantum physics, except he never accepted quantum physics. He always thought it was a terrible, terrible mistake, even though he essentially, kind of around the edges, thought of it.